Welcome to your second set of metabolism and enzyme notes. We're going to start on the side with this graph. And just to review really quick, we talked about kind of generically that you are going to have enzymatic reactions get using ATP that phosphorylate molecules, that activate molecules, et cetera, right? And we've talked about a couple last time, including kinase and phosphatase, right? So I'm just going to go ahead and add these up here. Grab this. So just for some examples of enzymes that we've talked about, kinase is going to add phosphate groups. Let's see if I can get this out of here. Adds phosphate groups, phosphatase removes phosphate groups. And then we have talked about some more. When we did the digestive system, we talked about lipase, which digests lipids, amylase, which digests starch, pepsin, which is one that digests proteins, trypsin also does that, nucleases, which digest nucleic acids. So there's a whole bunch of enzymes that we've talked about that you're already familiar with. So here's how they kind of work. So every reaction has a certain amount of energy that it needs put in beforehand to achieve the reaction. It's called the activation energy, right? Think of it like pushing a boulder up a hill. You have to push it up the hill before it can roll back down. Similar thing with reactions, right? In this graph, this is without a catalyst. So this is just if a reaction is going to happen without any help, it needs this much energy, right? Enzymes lower the activation energy, right? So if we're drawing this visually, the hill that has to be overcome, the amount of energy that has to be achieved before the reaction can go is significantly less. So this is the amount of activation energy needed with, I'll do W/ for an abbreviation, with the enzyme. And this is why enzymes speed up reactions. It can take hours and days and weeks potentially for a cell or a system to have enough energy to push a reaction through to completion without an enzyme. But with an enzyme, you can achieve these reactions much, much quicker, fractions and fractions of a second. Enzymes work incredibly fast, and it's because they have significantly less energy they need to gather up, and they've lowered the activation energy. In this drawing, the products have a lower energy, so let's go ahead and just review that really quick. In this case, this is a negative change in free energy, negative delta G. So catalysts are going to lower the activation energy. We've gone over some enzymes. Those are going to be proteins. There are also ribozymes that can serve as catalysts. Those are going to be made of RNA. So not all catalysts are enzymes. Some are actually made of RNA. These are called ribozymes. Chemistry, because you're not using body systems, is usually going to talk about things like inorganic compounds or elements being catalysts. So a common one that you might be familiar with, this is also like if you're a car person, which I am not, but if you are aware of the catalytic converter, it's called this literally because it has a catalyst in it. It's not an enzyme or a ribozyme, it's because it actually has platinum. So fun fact, but in chemistry, these are usually inorganic compounds or elements. In biology, they are going to be enzymes or ribozymes. All right, so let's scoot over to the side here, which is going to make me pick a different page. Where's the next page? Here's the next page. So we're going to go up to the top here, right here. And we're going to talk about how enzymes work. Remember that enzymes are not used up. They are reusable, they don't get destroyed in a reaction, and they are substrate specific. And that's because of the shape of the active site. Remember, that's the most important part of the enzyme. And this is why they're very, very picky. They're picky because they're like a lock and key mechanism. Remember, your car key can open your car lock, your house key can open your house lock, but they can't open up each other because they don't fit. It's all about the shape, and that's true for enzymes as well. So here we have an enzyme. I'm just kind of doing a little schematic here. They really have a 3D shape and structure that you guys are familiar with because of, you know, secondary and tertiary and even quaternary folding and structure and all that. But here it is as a flat little shape. Here's the active site right here. And notice that it fits this substrate beautifully. Right, so these are specific to each other. And when the enzyme is kind of bouncing around diffusing in the cell and the substrates are bouncing around diffusing in the cell and they find each other, remember, they do find each other from diffusion. This is not, they're not like heat-seeking missiles. They don't like have targets out for each other. They are simply diffusing, and if they happen to bounce around in the right spot, the substrate will fit into the active site. The enzyme is basically providing a reaction location. It's saying, hey, I heard you need a reaction site. Here it is. Let me provide the space you need. And this is why enzymes are so effective at catalyzing and speeding up reactions and whatever your products are out. Right. We're going to talk about this little weird looking indentation over here in a second. Right. But what I want you to know is that enzymes are not always on. Enzymes are not always on. We're going to look at cases where they are initially off. But assuming an enzyme is on, there are instances where you do want to turn it off. You don't necessarily want to use up all the substrates. You don't necessarily want any particular reaction just happening ad infinitum. You want to be able to regulate your metabolism as a cell. So you do want to be able to turn enzymes off. So there are two main ways to do this. One main way to do this is called competitive inhibition. Competitive inhibition. So basically what this is you have your enzyme that has its specific substrate, but the substrate can't bind because there's an interloper. There's a inhibitor molecule that it kind of fits, but it doesn't perfectly fit, but it blocks the substrate. So it fits well enough to block the substrate. So it physically, I'm going to go ahead and write this. It physically blocks the substrate. Physically blocks the substrate from entering the active site. It competes with the substrate, hence competitive. And it inhibits it. It prevents it from binding, so it's competitive inhibition. Not very clever naming, but it tells you exactly what goes on, right? And remember that these molecules find each other. The enzymes and the inhibitors and the substrates find each other because they are diffusing around the cytoplasm. They're not like looking for each other or anything like that. It is random motion. This is diffusion of molecules. Right, so if you produce a lot of inhibitors, so if you increase the concentration of inhibitors, so I'm going to draw this little triangle because that's the shape of my inhibitor. So if we increase the concentration of my inhibitors, that means, therefore, you're going to get more blockage. So if a cell needs to stop an enzyme from running a reaction, it's going to produce these inhibitors. The more inhibitors are diffusing and bouncing all willy-nilly around the cell, the more they're going to encounter the active site of an enzyme, and the more common or the more frequently they're going to inhibit and block and compete with the substrate for that location, and they're going to block it, right? And the opposite's the case. If you reduce the amount of inhibitors, you're going to reduce the amount of times this blocks the substrate, and the enzyme is going to be able to catalyze more reactions. The other type of inhibition that you can turn off an active enzyme is called non-competitive. So we are going to inhibit, but we're not going to compete. This is where this little crook comes in, this little nook or cranny, whatever, that's what I meant to say. This is called the allosteric site. It's the star of the show in this example, hence it's called allosteric inhibition. So an allosteric site is going to have an allosteric inhibitor. This is some other kind of molecule that fits, it's almost like a second active site, although it's not the active site. But it fits in a similar way. So it's going to fit right into the allosteric site, and that is going to cause the active site to have a shape change. Shape change, shape change. That's going to prompt a mismatch between the active site and the substrate, and this substrate will not fit. So sad, too bad. Right. So those are the two ways that you can effectively turn an enzyme off. Other enzymes are by default off, and they have to be activated. They have to be turned on. So here's how to do that. Here we have an enzyme. That's our enzyme. And the default is that the substrate does not fit. For whatever reason, in this little schematic, just for this picture, I've kind of drawn this as like a little extra little pouch here. It's too big, it's too spacious, it doesn't quite fit in there, right? So what you have to do is you have to fill this gap. You have to fill this extra space. In this case, we're going to have to add what's called a cofactor or a coenzyme, this basketball-looking thing, right? So, and again, the shape is just, this is all, this is a model. They don't actually look like basketballs or hashtags with a circle around them. So here's the cofactor or coenzyme, and it's occupying that extra space. And look at that, now the substrate is able to fit. It's nice and happy, and we have successfully turned this enzyme on, right? So what are cofactors and coenzymes? Because they're not basketballs. Cofactors are usually minerals. They are inorganic. These are things like magnesium, iron. This is why if you take like vitamin supplements or mineral supplements, you have to consume these because they help regulate your chemical reactions. They serve as cofactors that help turn on enzymes, right? Fun fact, hemoglobin, which has quaternary structure of 4 different proteins. 2 are alpha. It's different than alpha helix, but they're called alpha proteins, and 2 that are beta. Every one of these components of hemoglobin, which carries oxygen in your bloodstream, has to have an iron in it. Because the iron actually bonds, the iron actually bonds to the oxygen. That's actually what's responsible for carrying the oxygen. You're kind of literally rusting iron in your bloodstream while you breathe, and that's how it works. But you need iron to do that. So just as a little aside example, the importance of minerals. Coenzymes are organic, and you can remember that these are organic because enzymes are organic, right? Enzymes are proteins that are a macromolecule that are organic. So that's how you can remember. These are your vitamins, right? Vitamin A, B, C, D, all that stuff. Again, this is why you would take supplements, because they help regulate reactions. All right, let's hop down here to the bottom. But for me, I have to go to a different page. Here it is. We're kind of back to the other side, just below where we were before. All right, I have space over here on the left. You're gonna probably have to do this somewhere else, maybe like off to the right, kind of up here in the upper right. I'm gonna do it over here on the left, because we're gonna draw some graphs. But in general, when you have an enzymatic reaction, you start with your substrates or your reactants. Those are synonyms, so you can pick either. And you end up with your products. And again, enzymes mediate this reaction. They facilitate the reaction, right? And to figure out the rate of a reaction, there are a couple things you can measure. And we're going to do this in the lab that I'm going to make a video of and we'll work on next week. You can measure the products or the substrates. So let's go ahead, and you're going to do this probably over here. I'm going to do it over here. Let's have time on the x-axis. Let's have products. That says products. I just ran out of space. We'll put substrates over here. Substrates will be a dashed line for the graph, and products will be a solid line. So as the reaction goes, you start with all of the substrates, right? You have all of these reactants kind of ready to be made into products. So your substrates are really, really high. As the reaction continues, you convert substrates into products. So over time, the amount of substrates decreases. The opposite is true for your products, right? You don't start with any products because you haven't done anything yet. So your products at time 0 is low, it's 0. But then as you convert substrates into products, you get more products as time goes on. So your products go up. If we were to graph the enzymes, what's happening to enzymes? Are they increasing or decreasing? Well, remember, enzymes don't get used in a reaction. They are recycled. So if you want to add another graph, again, probably over here somewhere, the level of enzymes is going to be constant. I'm just going to abbreviate enzyme. That means enzyme. ENZ. The amount of enzyme is constant. They don't get reused. All right, so let's look at, I can't really scroll over, that's okay. Let me just move this. Let's look at how to calculate the rate of reaction, because we are going to do this in the lab next week. So again, you can measure the products, you can measure the substrates. In the lab, we're going to measure the products. In this graph over here, we're going to measure the products. And one way you can do this is to do it just the way you would do it in math. You would calculate the rise over the run. You would calculate the slope. So at 1 minute, you have that much product, right? At 2 minutes, again, I'm over kind of here on the bottom right. At 2 minutes, you have that much product. At 3 minutes, you have that much, and so on. Right, and eventually you plateau, you kind of flatline. So you'll notice that you eventually flatten out. That's because you've just run out of substrates. You've used them all, and you've made as many products as you're going to get with the substrates that you had. So you will eventually kind of flatline and plateau up here and max out. So the calculation for this, again, is just the same as it is in math. It's rise over run. It's y over x. So it's the amount of product over the amount of time. And what you're going to see, and you'll see this during the lab also, is that your rate of reaction is quickest early on. It's going to be pretty quick in the first couple of minutes, and then as you use your products, as you use your substrates and you make your products, that reaction will slow down. Not because the enzymes are broken or anything like that, but simply because you've just used up, you're using up more and more of your substrates, and because there are less substrates bouncing around in that solution, be it the cytoplasm or a test tube, they're just going to encounter the enzymes less frequently, and you're going to get less product. And for the lab, we are going to focus on the first minute or two for our calculations. Last little bit here, let me zoom out, and where it's going to be the last thing we have to do here, it is. So let's look at 3 variables, and then we'll wrap up here that affect the rate of enzyme reactions. One is temperature, one is pH, and then over here on the right is salinity. So temperature first. Every enzyme has an optimal temperature that it functions best at. For humans, it's going to be our body temperature, just because that's our temperature environment. So if you drop down here, you're going to get about 37 degrees Celsius. You should be familiar with that number because that is body temp. It's about 98.6. And there's kind of an optimal rate of reaction. right? Whatever this rate is, it's some kind of arbitrary, unit. When you increase temperature, you denature the enzyme, right? You increase the kinetic energy. That's going to put stress on the bonds within that protein, specifically the hydrogen bonds, and they're going to break. They're going to break, and that's why the enzyme will denature in high temperatures. So I'm going to say H bonds break. Remember, you're breaking the secondary structure of that protein, of that enzyme. That's where the hydrogen bonds are. If you go too low, if you decrease the temperature, you're slowing down the collisions, right? You're decreasing kinetic energy. You're not breaking hydrogen bonds, you're just decreasing total movement, which means your reactants and your enzymes will encounter each other less frequently, and their production of products, the rate of product formation, will decline, will decrease, right? It is possible to denature under very, very cold conditions, but what usually happens is you hit 0 degrees Celsius first, and the cytoplasm freezes, right? So for all intents and purposes, cold temperatures simply slow down collisions. So I'm going to go ahead and just type that because it's a little lengthy. I'll say cold temps slow collisions, low product formation. I'll say collide less often. That's the key point. They collide, the substrates and the enzymes collide less often. All right, pH and salinity are the same story. They have optimal pH or optimal salinity. Again, for your body, most of this is going to be 7. However, it can be different, like in the stomach where it's 2 because pepsin functions to break down proteins in an environment of hydrochloric acid. But most of the time it is going to be pH 7, right? Same thing with salinity. There's kind of an optimal salinity, and if you deviate too far either way, you're going to denature the protein. You're going to denature the enzyme, right? And the reason for this is to just review. Go down here. Let's draw secondary structure. So here's a protein. I'm drawing beta pleated sheets. So these are beta pleated sheets. And remember, these are secondary structures, so they're held together by hydrogen bonds. So let's draw some hydrogen bonds. So got a partial negative over here and a partial positive over there, and they're attracted to each other. So there's a hydrogen bond. Let's add one over here. So there's a partial negative, there's a partial positive. There's a hydrogen bond, and oh heck, let's do another. Here we go. There's another. All right. These are maintaining secondary structure. If you, and by the way, this is existing in the cytoplasm of a cell, and the cell has pH, which means it has a concentration of hydrogen. So there is a default kind of normal level of hydrogens that these folds and hydrogen bonds occur in. It's not like there are no hydrogens out here. But the point is that when you get too acidic, right, when you decrease the pH, you're adding too many protons. You're adding too many hydrogens, right? So you're adding. I'm going to add a whole bunch of protons all over the place. Look at all these protons. And what's going to happen if you get too acidic? Well, what's going to happen is eventually this guy, this positive, slightly positive charge, is no longer the closest slightly positive charge because there's so many protons all over the place. There are going to be closer protons, like this one right here. So this negative charge says, ooh, I would much rather form a hydrogen bond with you, not this one over here, and this bond breaks, right? Ooh, this one, I would much rather form a bond with this one right here, much, much closer. The connection's stronger, the attraction's stronger, like physically, there's less distance, so that bond breaks. Same thing with going to basic. All right, so here we're adding more protons. When you get too basic, you're adding more hydroxide ions. And it's the same phenomenon, but with the positive charges. Right? So that's how you denature, or why you denature an enzyme with pH, with changes in pH. Salinity is a similar story, right? Because when you have salts, they ionize. And it's now you're in the same position, right? Now you have sodium as a positive charge, chloride ion with a negative charge, and you're gonna have a very, very similar story. Also with salinity, you have to account for the fact that you have ionic bonds in the tertiary structure that have a full charge that are going to be attracted to the full charges of either of these two ions, right? So this is how pH and salinity, either too much salinity or too few salts, body salts, can actually end up denaturing enzymes and dropping the reaction rate. So I hope that helped. I think that pretty much covers everything, and I will see you guys in the lab next week.